Hi, Steve Ellingson here from Virginia Tech. My talk is on pattern synthesis for complicated arrays. Pattern synthesis means that you have an array and you're trying to find the excitations or the weights or the beamforming coefficients, however you'd like to refer to those quantities, that give you a specified pattern. This problem is very well understood for simple arrays. Any decent textbook will tell you how to obtain certain types of patterns given a simple array. By simple array, I mean something like a uniform linear array, abbreviated here as ULA, having isotropic element patterns. Generally, the answer given in textbooks is some form of Fourier analysis, or perhaps something like the Dolf-Chebyshev or Taylor techniques. On the other hand, you might have an array with non-uniform spacings or non-uniform element patterns, perhaps due to strong and disorderly mutual coupling. Or perhaps you have an aperture which is not fully sampled in the Nyquist sense. For example, element spacing significantly greater than 1/2 wavelength. In these cases, the options for pattern synthesis are not so clear. Let me show you an example of such an array. Here's an example of what I'm calling a complicated array. The positions of the elements are shown in blue. The element spacings are non-uniform. They vary between 0.4 wavelengths towards the center of this array to 1.2 wavelengths near the ends. The element patterns are half cosine functions, and each element points in a different direction as indicated by the red arrows. I'll leave it to your imagination to consider the application for such an array or where such arrays come up. This array defeats the common methods for pattern synthesis previously identified. The aim of this presentation is to show a simple method for pattern synthesis that can be used for such an array. We begin with a mathematical problem statement. The pattern of an n-element array, that is, an array having n elements, can be expressed as the sum over those elements of the excitations, identified here as b sub n, times the element patterns, expressed here as f sub n, whose argument r hat is the direction in which the pattern is evaluated, times a geometry-induced phase indicated by this factor. Here p sub n is the position of the nth element, and beta is the phase propagation constant, that is 2 pi divided by wavelength. In this framework, pattern synthesis means selecting the excitations such that the array pattern f that you get equals, as closely as possible, some specified or desired pattern, which we're indicating here as G. Of course, equivalence between F and G is generally not possible. That is, it's possible only in certain very limited cases. In general, it's not possible simply because it's an overdetermined system. Matching every point in a pattern typically will require more elements and subsequently more excitation coefficients than you have available in the array. So solutions to pattern synthesis problems are almost always approximate. One way that the problem can be attacked is in terms of satisfying exactly a discrete number of constraints. So for example, you could attempt to exactly match a discrete number of points in the pattern, which is possible if you have a sufficient number of excitation coefficients. And as mentioned previously, another approximate approach would be to use the Fourier transform relationship between the excitation coefficients and the array pattern. Approximate Fourier transform solutions are well known for certain special cases. For example, the ULA, where all the element patterns are identical, nominally isotropic. In this presentation, we want to generalize this idea to complicated arrays, where we do not necessarily have uniform spacings, uniform element patterns, and so on. The strategy here is to reduce this equation to a linear system of equations. So in other words, what we'd like to do is reduce this equation, which is continuous in pattern direction, to a discrete set of equations, and then somehow attempt to solve those equations for the excitations. Beginning with the array equation, we first multiply both sides by the conjugate of the quantity indicated in the square brackets, in which the subscript n is replaced by the subscript m, and where we will later let m go from 1 to the number of elements, that is big N. Next, we integrate over both sides over a sphere that encloses the array. Here, d omega is the differential element of solid angle, that is, sine theta, d theta, d phi. This eliminates the dependence on pointing direction. Exchanging the order of integration and summation on the left, we obtain the equation shown at the bottom of the slide. Note that we now have a simple linear equation with n unknown values, that is, the b sub n's. Of course, we actually have big N such equations, since m can go from 1 to n. Thus, we have a linear system of n equations with n unknowns, allowing a simple solution for the b sub n's. Summarizing the result from the previous slide, we use the notation a sub mn and c sub m to compactly represent the two integrals. It's worth noting that the n squared values of a sub mn do not depend on the pattern specification g. Instead, the a sub mn's serve as a compact description of the geometry of the array, and this can be pre-computed. The n values c sub m, on the other hand, serve to represent the pattern specification, that is g, in the same compact representation. Of course, all this is conveniently represented in matrix notation, as shown here. So the n by 1 vector of b sub n's, the excitations we seek, is given by right multiplying the inverse of the n by n matrix A by the n by 1 matrix C. This solution has a nifty linear algebraic interpretation that goes like this. This is a projection of the compact representation of the array specification onto the space of similarly represented patterns that can be supported by the array. Okay, now a demonstration. We'll be using the array described earlier in the presentation. For this first demonstration, the pattern specification G will be an impulse function in the direction indicated by the green arrow, which is pointing in the phi equals 15 degrees direction. By impulse function, I mean a beam with 0 beam width and no side lobes, such that we presumably achieve the highest possible directivity. Such a beam is described in the traditional way as a mathematical impulse function. As is customary with impulse functions, we include the condition that the integral over the sphere containing the array yields a finite value, in this case 1. This definition of the impulse function allows us to compute the c sub m's. In fact, it makes the integral quite simple. Obviously, since the array is finite, we do not expect to achieve this pattern. Nevertheless, we would hope to see maximum directivity in the specified direction. And also, I'll point out that it's simple to determine the b sub n's that yield maximum directivity in the specified direction. That is, that's the simplest possible beamforming operation. That simple method of determining the b sub n's will serve as a sanity check. Here's the result. The horizontal axis is direction in the plane of the array. The vertical axis is normalized pattern in dB. The blue curve is the result from the proposed method, which thankfully yields a very narrow beam in the specified direction. The red curve is a result for the easy-to-compute phase-only beamforming coefficients that yield maximum gain in the specified direction, subject to no other constraints. So blue is the proposed method, and red is the result from simple phase-only beamforming. As expected, the main lobes are very similar, and also the peak side lobe levels are similar. The details of the side lobe structure are somewhat different, and this is to be expected since the methods themselves are somewhat different. Regardless, the proposed method seems to be working. For a demonstration of how the technique might work in a practical application, consider the second example. Here the array itself is unchanged, but now the pattern specification is the sector beam, indicated in green. The sector beam is uniform over the indicated 30-degree span and is 0 elsewhere. And of course, this cannot be achieved exactly since the array is finite. If the array were a ULA with isotropic elements, we could use a Fourier transform technique, but that straightforward technique does not work in this case, and so it is an application for the technique that's been developed here. Let's turn this method loose on this problem and see what happens. Here's the result. Once again, the horizontal axis is direction in the plane of the array, and vertical axis is normalized pattern dB. Now the red curve is the pattern specification G, that is a value of 1 when phi is between 0 and 30 degrees, and 0 otherwise. The blue curve is the result from the proposed method. Once again, the proposed method seems to have worked as well as can be expected given that the array is finite. Furthermore, note that the side lobes are quite low despite the fact that this technique makes no explicit attempt to minimize the side lobes. Thus, the proposed method seems to be useful. So here are some concluding remarks. A simple method for pattern synthesis has been described and demonstrated. This is applicable to arrays regardless of array geometry, element spacing, and element patterns, and there are no restrictions on the pattern specification. Also, I should note that I think it is unlikely that this method is truly novel, since the derivation is very simple and is a somewhat obvious thing to try once the problem is posed. I've made some effort over the years to look for this method in the literature, but so far have not seen it. And since it is somewhat useful, I thought I would share it. If anyone listening has seen it, I'd be interested in hearing from you. It's important to keep in mind that nothing is being optimized by this method. In particular, it is not deliberately minimizing pattern error. As a result, unintended consequences are possible. One possible way to use this technique would be as a starting point for an iterative search. So this technique could be used to get close to a specification, and then to use other techniques, perhaps just simple numerical iteration, to obtain a pattern that is qualitatively closer to the specification. You can apply additional guidance to the technique simply by adding any number of additional equations in the linear system A, B equals C that was derived earlier. This is straightforward to do because the equations are all linear in the excitations. So for example, you could come up with equations that describe pattern constraints or constraints on the derivative of the pattern, and then add those to the linear system. Of course, in this case, the constraints will not be exactly satisfied, since at that point the linear system will be overdetermined. Nevertheless, this could be used to nudge the solution in a direction that is deemed useful. Just to elaborate for a moment on this extended method, consider this. Here's the expression for array pattern from earlier in the presentation. For brevity, let everything other than b sub n in each term be represented by the factor h sub n, which is a function of direction. Since this expression is linear in the b sub n's, it can be simply tacked on to the bottom of the linear system, as indicated here. Here the top three lines comprise the original n by n system, and the bottom line represents a constraint on the pattern in the direction r hat sub naught. And you can continue to do this for any number of additional constraints. The system is now overdetermined, so the solution is now in terms of a pseudo-inverse as opposed to a simple inverse. But otherwise, there's no additional difficulty in obtaining a solution. However, we must remember that the solution that is obtained minimizes mean square error with respect to the c sub n's and the original constraints. That is, the original constraints will not normally be exactly met. Nevertheless, this should be effective in nudging the pattern towards the desired shape. That concludes my presentation. Thank you for listening.